So, we will continue with this. I hope you tried to solve this equation. It is not very difficult, it is just simple log equation, and what you will get over here should be like this. I had already given the limits, and therefore, from that limits you should get or in other words P is equal to P as a function of H is equal to P naught exp So, this is the form of the pressure as a function of height h. So, if in a single compact you move from a particular height. So, let us say if you put h equal to 0, which means you are looking just at the surface. So, this becomes e to the power 0 equal to 1. So, it is equal to P naught. So, just at the surface it is equal to P naught as you would have expected, and when you move away from that surface, the point at which the pressure is being applied into the compact, then the pressure exponentially decreases. And at this point let me show you how the pressure variation looks like. So, this is P h by P naught, and let us say this is on the x axis we have thickness by diameter. So, this is nothing but h by d, and over here you have 1.0, meaning pH is equal to P naught, that is the maximum pressure that is being applied is what is you see that you would see at just at the surface, which will be at this point, and as you keep going on what you would expect is that it exponentially decreases, and this is what you would see something like this. So, your pressure is continuously decreasing. Not only that, it also says that if you have a much thicker sample, a much thicker material, then the pressure difference will be large. So, for example, if I were to draw or have two different compacts, let us say I have one compact which is like this and another compact which is much thinner. So, here the total H, the uppercase H is large, here the uppercase H is small. So, the pressure drop or the pressure change and the pressure gradient from here to here is very large. Here the total pressure change delta P is much smaller. And what does that imply? What do you mean when the pressure change is very large or the pressure drop is very large? It means that the density would also change accordingly. So, here you will get higher density and it will keep decreasing and you will get much lower density in the lower region. So, but here the difference would be much smaller. So, here whatever density you get, it will not be much, or here it will not be much smaller than the pressure, than the density that you get over there, and that has an implication in the shrinkage during centering. So, if you were to center this, it will probably center something like this. Why have I drawn like this? So, you will have, of course I am drawing it in an exaggerated way and there is no line over here. So, let me remove this. What I am trying to show here is that the shrinkage would be larger in the region where the pressure was smaller or the density was smaller. So, the relative density in this region was smaller. So, it was not packed or compacted to that so efficiently, and therefore, shrinkage here would be larger. So, the problem that arises when you do not have proper pressure distribution is that it leads to non-uniform density distribution, and non-uniform density distribution means uneven shrinkage in the sample or distortion in the sample. So, a component may not come out right. So, these are some of the things that you have to be aware when you are using powder processing. So, now this now having said this, that there will be non-uniform shrinkage and because of this non-uniform pressure distribution, the obvious question is how to get rid of it. We have seen that whenever you will have a pressure, whenever you are applying a piston and the pressure on it, there will be a pressure gradient, and pressure gradient will lead to this density gradient and hence shrinkage. So, how to get rid of it? One way is already what I have shown over here. So, you see that if you have very long in the z direction, then it will have larger chance of shrinkage. Over here the shrinkage will be much smaller. So, if you were to make this, the shrinkage would be so small that it may be within the tolerable limit, and that is one reason you see that most of the time in powder processing we use only 2.5 dimensions. That is, in the third dimension you do not have much larger length or you do not have much height of the component, because you want to keep it smaller. Another thing is, if you were to use this kind of system of powder processing, let me at this stage draw how a schematic density distribution would look like when you have a system like this. So, it will be, so let us say we are looking at the compact over here, and if we were to look at it, because of some other factors, like because there is friction also on the surface, the density distribution would look like this. So, for example, let us say this will be very high density, this will keep on reducing, and it may reach even something like this. So, these are some relative comparison of that variation in density. So, this is very dense and slowly the density has reduced. However, if you were to get the same dimension and you want less pressure distribution and less density distribution, there is one way, and that is to use a double ended piston. So, this is a single ended piston. Now, you can have so this is the compact that you want to use. So, you will have this piston moving in, this piston moving in, and therefore, the relative motion of the particles over here becomes smaller, and therefore, the overall average motion or the average movement of the particle is smaller, and hence the friction faced by them would be smaller. And if you were to look at the pressure distribution, or sorry, the density distribution for this, it may look something like this. So, now here you will have very high density 5.2, let us say, because that was 5.5. So, if we have 5.5 over here, it will also be 5.5 here by symmetry, simple symmetry, because you are applying pressure from here and from here. So, the density would be 5.5 here, and let us say it gets down to 5.2 over here. So, by this will also be 5.2. So, now you see it is the same, we are using the same dimension, compare it. Over here it drops from 5.5 to 4.2, in this case it drops from 5.5 to just 5.2, and therefore, you have much smaller density distribution in this case than in this case. So, this is a more preferred way if you want to have much more dimensional accuracy. Now, when we are doing this compaction, there is also a phenomena called as end capping. But before that, let us come back to our slide and let us see what we have understood about friction analysis. So, friction causes varying pressure across the pattern along the depth as well as along the radius. We have not looked in detail the variation of pressure in the along the radius, but that is also present over there, because friction will also be acting over here. The pressure variation across the part leads to green density variation, which is what is more of concern, and the density gradient, although it is not as large as the pressure gradient. So, maybe your pressure is varying by 20%, but the density may change by only few percent, but that is still enough to cause differential shrinkage. So, but it is still detrimental to the overall shape. So, density gradient can cause varying shrinkage. So, this is what we have learned so far. Next is when we are doing compaction, there is still another important aspect to this, which is called end capping phenomena. This is a simple concept, and if we were to explain it simply it will come out like this. So, let us say you have again a compact, there is a pressure variation along this, we have already seen like this. So, there is a pressure variation and also along the radius there is a pressure variation. So, if you were to look at pressure variation like this, so on the edges you have the applied pressure, but towards the center you have a peak pressure. Now, because of this two directional pressures, one from the surface and one from the side, there is a variation in the pressure because of this, and also because when once you press it and then relax, the material tries to come back to its original space, original shape, or it relaxes a little bit. So, because of this phenomena and the fact that there is shearing, compressive plus tensile stresses, so these two facts, the fact that there is pressure variation along the because of friction along the edges and because there is friction along the surface, there is another pressure distribution, and the fact that after you have compressed and you remove the piston, the material or the component tries to relax, and hence there is some amount of tensile forces. So, the two things add together and lead to a shearing phenomena. So, a small region just near the top, it breaks off. So, it will look like and it is, as you can see, it is like a cap shape, and that is why it is called end capping phenomena. So, this is also important, particularly when you are applying very large forces, large compaction pressures. So, this is another reason why we should not apply very large compaction pressure. You have to optimize based on the plot that we saw earlier, where you get saturation in the relative density, and also by finding out when the pressure becomes so large that you start to see end capping phenomena. So, let us get back to the slide. So, at high pressure, cup and cone type of fracture can occur, particularly in brittle metals and ceramics. So, this is a phenomena that is more common in brittle metals and ceramics, not so much in ductile materials. Because of pressure gradient, there is shearing taking place. So, one of the reasons to add to this is the pressure gradient, as we said. During release of pressure, top edge springs back a little bit. So, there is a shearing and tensile force leading to cracking near the top edge close to the die wall, and this is what is called as the end capping phenomena. This limits the maximum compaction pressure that can be used. Exact value of maximum pressure would depend on the friction along the die wall. So, this you will have to, like I said, you will have to look at what is the relative density you are able to get and what is the friction condition that leads to this kind of detrimental phenomena. So, that will limit what is the maximum pressure you can apply. Now, having said that, there is another small bit of information that we should look at before we move on from the compaction, powder compaction process. That is a little that is about tooling. So far we have assumed a simple shape, two-dimensional shape. Now, let us say that the shape is not two-dimensional and it has some, you can say, what is called as two levels. So, to begin with, let us say this is a shape. So, it is called a two-level shape because it has two levels. Now, for sake of simplicity, I will assume that this is L1 and this is 2L1. Now, if I want to make a component like this two-level shape, so if I am using a simple geometry for powder processing, that is just single piston from both sides, that is double ended but single piston on each side, then I will have to start with a material shape like this. So, let us say I start with 4 L1. Now, the piston that I will have will in the end will also have to have a difference similar to that what is in the final component, which is 2 L1 minus L1, that is a difference of L1. So, to begin with, the piston must have a difference of L1. So, if this is L1, then this distance must be 3 L1. Now, from here it gets compressed to this. So, now let us look at the two regions separately. So, what is the, so this is one region and this is our second region. What is the compression that you get in over here? Let us compare with the compression that you get over here. Over here you are getting 4 L1 to 2 L1, implies 2 times of compression. Here you are getting compression from, let me write it in different color to ensure that we do not mix up. So, here we are getting from 3 L1 to L1, means 3 times compression. So, you see, for a simple shape, although it is very simple in many sense, we are getting differential compression over here, which would again mean different density in this region and different density in this region, and that is because we are using a single piston on each side. So, let us say this is our piston. I will use since the piston is very simple like this, which will have a constant travel length. What is the travel length over here? So, it starts from here. So, therefore, it comes all the way 4 L1 to 2 L1. So, the total travel length is L1. You can look at over here or over here. So, it goes from 3 L1 to L1. So, the distance that it travels is 2 L1. So, in the both the cases travel length is 2 L1. Because of this limitation, where that is you have to have similar traverse length, we get different compression ratio. Now, if you want to improve it, what is the way? It is that you design your tool, that is your pistons, in a way that they can travel different lengths. So, what you can do, let us again draw our shape that we were looking at. Now, here let us say we start with like this. So, here we have a piston which has two parts. So, these two parts, let us say, are able to move independently. Okay. Now, again I will give a distance. So, we already have said this is 2 L1, this is L1, and if we want the same compression ratio, so if it is going from 4 L1 to 2 L1, this should go from 2 L1 to L1, that is the total length that we are talking about. So, to begin with, the powder compact is 4 L1 length and it gets compressed to 2 L1. Here it is 2 L1 and getting compressed to L1. So, if we talk about compression, four L1 to 2 L1 on this side, and over here 2 L1 to L1, that is 2x. So, now we are safe, we have equal amount of compression on both sides. What is different here is the total travel. Here it travelled 4 L1 minus 2 L1, which is equal to 2 L1. So, this is travel, how much the piston has to travel, 2 L1. Here it has to travel from 2 L1 to L1, which is equal to L1. So, the two sides of the pistons, these two parts, these are one part, this is one part, there is another part, they will have to travel different lengths. So, this is the kind of technology or ideas or innovation that you will have to apply depending upon your component that you are trying to create. Even for a simple geometry where we have just two levels, you can see that we have to think about what should be the travel length, what should be the compression ratio, so that you can get very good dimensional accuracy. So, that is all we will look at in this aspect of powder compaction. There are of course a lot more things. If you want in more detail, you can always visit the book. Thanks.